Part 2, Chapter 2 of A Popular History of Astronomy during the 19th Century. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. A Popular History of Astronomy during the 19th Century by Agnes Mary Clerke. Chapter 2, Solar Observations and Theories, Part 2. By its rotation, the Sun itself offers opportunities for bringing the stereoscope to bear upon it. Two pictures taken at an interval of 26 minutes show just the amount of difference needed to give, by their combination, the maximum effect of solidity. De la Rue thus obtained in 1861 a stereoscopic view of a sunspot and surrounding faculae, representing the various parts in their true mutual relations. I have ascertained in this way, he wrote, that the faculae occupy the highest portions of the Sun's photosphere, the spots appearing like holes in the penumbrae, which appeared lower than the regions surrounding them. In one case, parts of the faculae were discovered to be sailing over a spot apparently at some considerable height above it. Thus, Wilson's inference as to the depressed nature of spots received, after the lapse of not far from a century, proof of the most simple, direct, and convincing kind. A careful application of Wilson's own geometrical test gave results only a trifle less decisive. Of 694 spots observed, 78% showed, as they traversed the disk, the expected effects of perspective, and their absence in the remaining 22% might be explained by internal commotions producing irregularities of structure. The absolute depth of spot cavities, at least of their sloping sides, was determined by Father Secchi through measurement of the parallax of profundity, that is, of apparent displacements attendant on the Sun's rotation due to depression below the Sun's surface. He found that in every case it fell short of 4,000 miles and averaged not more than 1,321, corresponding on the terrestrial scale to an excavation in the earth's crust of 1 1/5 miles. Of late, however, the reality of even this moderate amount of depression has been denied. Mr. Hallett's persevering observations, extending over a third of a century, the results of which were presented to the Royal Astronomical Society in December 1894, availed to shatter the consensus of opinion which had so long been maintained on the subject of spot structure. It has become impossible any longer to hold that it is uniformly cavernous, and what seem like actually protruding umbrae are occasionally vouched for on unimpeachable authority. We can only infer that the forms of sunspots are really more various than had been supposed, that they are peculiarly subject to disturbance, and that the level of the nuclei may rise and fall during the phases of commotion like lavas within volcanic craters. The opinion of the Kew observers as to the nature of such disturbances was strongly swayed by another curious result of the statistical method of inquiry. They found that of 1,137 instances of spots accompanied by faculae, 584 had those faculae chiefly or entirely on the left. 508 showed a nearly equal distribution, while 45 only had fasculous appendages mainly on the right side. Now, the rotation of the Sun as we see it is performed from left to right, so that the marked tendency of the faculae was a lagging one. This was easily accounted for by supposing the matter composing them to have been flung upwards from a considerable depth, whence it would reach the surface with the lesser absolute velocity belonging to a smaller circle of revolution, and would consequently fall behind the cavities or spots formed by its abstraction. An attempt, it is true, made by M. Wilsing at Potsdam in 1888 to determine the solar rotation from photographs of faculae had an outcome inconsistent with this view of their origin. They unexpectedly gave a uniform period. No trace of the retardation poleward from the equator shown by the spots could be detected in their movements. But the experiment was obviously inconclusive, and M. Stratonoff's repetition of it with ampler materials gave a full assurance that faculae rotate like spots in periods lengthening as latitude augments. The ideas of M. Faye were on two fundamental points contradicted by the Kew investigators. He held spots to be regions of uprush and of heightened temperature. They believed their obscurity to be due to a downrush of comparatively cool vapours. Now M. Chacornac, observing at Villeurbanne, March 6, 1865, saw floods of photospheric matter visibly precipitating themselves into the abyss opened by a great spot, and carrying with them small neighboring maculae. Similar instances were repeatedly noted by Father Secchi, who considered the existence of a kind of suction in spots to be quite beyond question. The tendency in their vicinity, to put it otherwise, is centripetal, not centrifugal, and this alone seems to negative the supposition of a central uprush. A fresh witness was by this time at hand, the application of the spectroscope to the direct examination of the sun's surface dates from March 4, 1866, when Sir Norman Lockyer, to give him his present title, undertook an inquiry into the cause of the darkening in spots. It was made possible by the simple device of throwing upon the slit of the spectroscope an image of the sun, any part of which could be subjected to special scrutiny, instead of, as had hitherto been done, admitting rays from every portion of its surface indiscriminately. The answer to the inquiry was prompt and unmistakable, and was again in this case adverse to the French theorist's view. The obscurations in question were found to be produced by no deficiency of emissive power, but by an increase of absorptive action. The background of variegated light remains unchanged, but more of it is stopped by the interposition of a dense mass of relatively cool vapours. The spectrum of a sun-spot is crossed by the same set of multitudinous dark lines, with some minor differences visible in the ordinary solar spectrum. We must then conclude that the same vapours, speaking generally, which are dispersed over the unbroken solar surface, are accumulated in the umbral cavity, the compression incident to such accumulation being betrayed by the thickening of certain lines of absorption. But there is also a general absorption, extending almost continuously from one end of the spot spectrum to the other. Using, however, a spectroscope of exceptionally high dispersive power, Professor Young of Princeton, New Jersey, succeeded in 1883 in resolving the supposed continuous obscurity of spot spectra into a countless multitude of fine dark lines set very close together. Their structure was seen still more perfectly about 5 years later by M. Dunet, director of the Upsala Observatory, who traced, besides some shadowy vestiges of the crowded doublets and triplets forming the array, from the spots on to the general solar surface. They ceased to be separable in the blue part of the spectrum, and the ultraviolet radiations of spots show nothing distinctive. As to the movements of the constipated vapours forming spots, the spectroscope is also competent to supply information. The principle of the method by which it is procured will be explained farther on. Suffice it here to say that the transport at any considerable velocity to or from the eye of the gaseous material giving bright or dark lines can be measured by the displacement of such lines from their previously known normal positions. In this way movements have been detected in or above spots of enormous rapidity ranging up to 320 miles per second, but the result so far has been to negative the ascription to them of any systematic direction. Uprushes and downrushes are doubtless, as Father Corti remarks, correlated phenomena in the production of a sun-spot, but neither seem to predominate as part of its regular internal economy. The same kind of spectroscopic evidence tells heavily against a theory of sunspots started by Faye in 1872. He had been foremost in pointing out that the observations of Carrington and Spurrer absolutely forbade the supposition that any phenomenon at all resembling our trade winds exists in the sun. They showed, indeed, that beyond the parallels of 20 degrees there is a general tendency in spots to a slow poleward displacement, while within that zone they inclined to approach the equator, but their proper movements gave no evidence of uniformly flowing currents in latitude. The systematic drift of the photosphere is strictly a drift in longitude. Its direction is everywhere parallel to the equator. This fact being once clearly recognized, the solar tornado hypothesis at once fell to pieces. But M. Faye perceived another source of vorticose motion in the unequal rotating velocities of contiguous portions of the photosphere. The pores with which the whole surface of the sun is studded he took to be the smaller eddies resulting from these inequalities, the spots to be such eddies developed into whirlpools. It only needs to thrust a stick into a stream to produce the kind of effect designated, and it happens that the differences of angular movement adverted to attain a maximum just about the latitudes where spots are most frequent and conspicuous. There are, however, grave difficulties in identifying the two kinds of phenomena. One, already mentioned, is the total absence of the regular swirling motion in a direction contrary to that of the hands of a watch north of the solar equator, in the opposite sense south of it, which should impress itself upon every lineament of a sun-spot if the cause assigned were a primary producing and not merely, as it possibly may be, a secondary determining one. The other, pointed out by Young, is that the cause is inadequate to the effect. The difference of movement, or relative drift, supposed to occasion such prodigious disturbances, amounts at the utmost, for two portions of the photosphere 123 miles apart, to about 5 yards a minute. Thus the friction of contiguous sections must be quite insignificant. A view better justified by observation was urged by Secchi in and after the year 1872, and was presented in an improved form by Professor Young in his excellent little book on the Sun, published in 1882. Spots are manifestly associated with violent eruptive action, giving rise to the faculae and prominences which usually garnish their borders. It is accordingly contended that upon the withdrawal of matter from below by the flinging up of a prominence must ensue a sinking in of the surface, into which the partially cooled erupted vapours rush and settle, producing just the kind of darkening by increased absorption told of by the spectroscope. Round the edges of the cavity, the rupture of the photospheric shell will form lines of weakness, provocative of further eruptions, which will in their turn deepen and enlarge the cavity. The phenomenon thus tends to perpetuate itself until equilibrium is at last restored by internal processes. A sunspot might then be described as an inverted terrestrial volcano, in which the outbursts of heated matter take place on the borders instead of at the center of the crater, while the cooled products gather in the center instead of at the borders. But on the earth the solid crust forcibly represses the steam gathering beneath until it has accumulated strength for an explosion, while there is no such restraining power that we know of in the sun. Zöllner indeed adapted his theory of the solar constitution to the special purpose of procuring it, yet with very partial success, since almost every new fact has proved adverse to his assumptions. Volcanic action is essentially spasmodic. It implies habitual constraint, varied by temporary outbreaks, inconceivable in a gaseous globe such as we believe the sun to be. If the volcanic hypothesis represented the truth, no spot could possibly appear without a precedent eruption. The real order of the phenomenon, however, is exceedingly difficult to ascertain, nor is it perhaps invariable. Although in most cases the opening shows first, that may be simply because it is more easily seen. According to Father Sidgreaves, the disturbance has then already passed the incipient stage. He considers it indeed highly probable that the preparatory sign of a new spot is always a small, bright patch of facula. This sequence, if established, would be fatal to Lockyer's theory of sun-spots, communicated to the Royal Society May 6, 1886, and further developed some months later in his work on the chemistry of the sun. Spots are represented in it as incidental to a vast system of solar atmospheric circulation, starting with the polar out and up flows indicated by observations during some total eclipses, and eventuating in the plunge downward from great heights upon the photosphere of prodigious masses of condensed materials. From these falls result primarily spots, secondarily, through the answering uprushes, in which chemical and mechanical forces cooperate, their girdles of flame prominences. The evidence is, however, slight that such a circulatory flow as would be needed to maintain this supposed cycle of occurrences really prevails in the sun's atmosphere, and a similar objection applies to an anticyclonic theory, so to designate it, elaborated by Egon von Apolzer in 1893. August Schmidt's optical rationale of solar phenomena was, on the other hand, a complete novelty both in principle and development. Attractive to speculators from its recondite nature and far-reaching scope, it by no means commended itself to practical observers, intolerant of finding the all but palpable realities of their daily experience dealt with as illusory products of circular refraction. A singular circumstance has now to be recounted. On the 1st of September, 1859, while Carrington was engaged in his daily work of measuring the positions of sun-spots, he was startled by the sudden appearance of two patches of peculiarly intense light within the area of the largest group visible. His first idea was that a ray of unmitigated sunshine had penetrated the screen employed to reduce the brilliancy of the image. But having quickly convinced himself to the contrary, he ran to summon an additional witness of an unmistakably remarkable occurrence. On his return, he was disappointed to find the strange luminous outburst already on the wane. Shortly afterwards the last trace vanished. Its entire duration was 5 minutes, from 11.18 to 11.23 a.m. Greenwich time, and during those 5 minutes it had traversed a space estimated at 35,000 miles. No perceptible change took place in the details of the group of spots visited by this transitory conflagration, which, it was accordingly inferred, took place at a considerable height above it. Carrington's account was precisely confirmed by an observation made at Highgate. Mr. R. Hodgson described the appearance seen by him as that of a very brilliant star of light, much brighter than the sun's surface, most dazzling to the protected eye, illuminating the upper edges of the adjacent spots and streaks, not unlike, in effect, the edging of the clouds at sunset. This unique phenomenon seemed as if specially designed to accentuate the inference of a sympathetic relation between the earth and the sun. From the 28th of August to the 4th of September, 1859, a magnetic storm of unparalleled intensity, extent, and duration was in progress over the entire globe. Telegraphic communication was everywhere interrupted, except indeed that it was in some cases found practicable to work the lines without batteries, by the agency of the earth currents alone. Sparks issued from the wires, gorgeous aurorae draped the skies in solemn crimson over both hemispheres and even within the tropics. The magnetic needle lost all trace of continuity in its movements and darted to and fro as if stricken with inexplicable panic. The coincidence was drawn even closer. At the very instant of the solar outburst, witnessed by Carrington and Hodgson, the photographic apparatus at Kew registered a marked disturbance of all the three magnetic elements, while shortly after the ensuing midnight the electric agitation culminated, thrilling the earth with subtle vibrations and lighting up the atmosphere from pole to pole with the coruscating splendors which perhaps dimly recall the times when our ancient planet itself shone as a star. Here, then, at least, the sun was, in Professor Balfour Stewart's phrase, taken in the act of stirring up terrestrial commotions, nor have instances since been wanting of an indubitable connection between outbreaks of individual spots and magnetic disturbances. 4 such were registered in 1882, and symptoms of the same kind, including the beautiful rose aurora, marked the progress across the sun of the enormous spot group of February 1892, the largest ever recorded at Greenwich. This extraordinary formation, which covered about 1/300th of the sun's disk, survived through 5 complete rotations. It was remarkable for a persistent drift in latitude, its place altering progressively from 17 degrees to 30 degrees south of the solar equator. Again, the central passage of an enormous spot on September 9, 1898, synchronized with a sharp magnetic disturbance and brilliant aurora, and the coincidence was substantially repeated in March 1899, when it was emphasized by the prevalent cosmic calm. The theory of the connection is indeed far from clear. Lord Kelvin, in 1892, pronounced against the possibility of any direct magnetic action by the sun upon the earth, on the ground of its involving an extravagant output of energy. But the fact is unquestionable that, in Professor Bigelow's words, abnormal agitations affect the sun and the earth as a whole and at the same time. The nearer approach to the event of September 1, 1859, was photographically observed by Professor George E. Hale at Chicago, July 15, 1892. An active spot in the southern hemisphere was the scene of this curiously sudden manifestation. During an interval of 12 minutes between 2 successive exposures, a bridge of dazzling light was found to have spanned the boundary line dividing the twin nuclei of the spot, and these, after another 27 minutes, were themselves almost obliterated by an overflow of far-spreading brilliancy. Yet 2 hours later, no trace of the outburst remained, the spot and its attendant faculae remaining just as they had been previously to its occurrence. Unlike that seen by Carrington, it was accompanied by no exceptional magnetic phenomena, although a storm set in next day. Possibly a terrestrial analogue to the former might be discovered in the auroral beam, which traversed the heavens during a vivid display of polar lights, November 17, 1882, and shared, there is every reason to believe, their electrical origin and character. Meantime, M. Rudolf Wolff, transferred to the direction of the Zurich Observatory, where he died December 6, 1893, had relaxed none of his zeal in the investigation of sun-spot periodicity. A laborious revision of the entire subject, with the aid of fresh materials, led him in 1859 to the conclusion that while the mean period differed little from that arrived at in 1852 of 11.11 years, very considerable fluctuations on either side of that mean were rather the rule than the exception. Indeed, the phrase sun-spot period must be understood as fitting very loosely the great fact it is taken to represent, so loosely that the interval between two maxima may rise to 16½ or sink below 7½ years. In 1861, Wolff showed, and the remark was fully confirmed at Kew, that the shortest periods brought the most acute crises, and vice versa, as if for each wave of disturbance a strictly equal amount of energy were available, which might spend itself lavishly and rapidly, or slowly and parsimoniously, but could in no case be exceeded. The further inclusion of recurring solar commotions within a cycle of 55½ years was simultaneously pointed out, and Hermann Fritz showed soon afterwards that the aurora borealis is subject to an identical double periodicity. The same inquirer has more recently detected both for aurorae and sun-spots a secular period of 222 years, and the Kew observations indicate for the latter oscillations accomplished within 26 and 24 days, depending most likely upon the rotation of the sun. This is certainly reflected in magnetic and perhaps in auroral periodicity. The more closely, in fact, spot fluctuations are looked into, the more complex they proved. Maxima of one order are superposed upon or in part neutralized by maxima of another order. Originating causes are masked by modifying causes. The larger waves of the commotion are indented with minor undulations, and these again crisped with tiny ripples, while the whole rises and falls with the swell of the great secular wave, scarcely perceptible in its progress because so vast in scale. The idea that solar maculation depends in some way upon the position of the planets occurred to Galileo in 1612. It has been industriously sifted by a whole bevy of modern solar physicists. Wolff, in 1859, found reason to believe that the 11-year curve is determined by the action of Jupiter, modified by that of Saturn, and diversified by influences proceeding from the Earth and Venus. Its tempting approach to agreement with Jupiter's period of revolution round the sun indeed irresistibly suggested a causal connection, yet it does not seem that the most skilful coaxing of figures can bring about a fundamental harmony. Carrington pointed out in 1863 that while during 8 successive periods from 1770 downwards there were approximate coincidences between Jupiter's aphelion passages and sun-spot maxima, the relation had been almost exactly reversed in the 2 periods preceding that date, and Wolff himself finally concluded that the Jovian origin must be abandoned. M. Duponchel's prediction, nevertheless, of an abnormal retardation of the maximum due in 1881 through certain peculiarities in the positions of Uranus and Neptune about the time it fell due, was partially verified by the event, since after an abortive phase of agitation in April 1882, the final outburst was postponed to January 1894. The interval was thus 13.5 instead of 11.1 years, and it is noticeable that the delay affected chiefly the southern hemisphere. Alternations of activity in the solar hemispheres were indeed a marked feature of the maximum of 1884, which in Mr. Fay's view derived thence its indecisive character, while sharp, strong crises arise with the simultaneous advance of agitation north and south of the solar equator. The curve of magnetic disturbance followed with its usual strict fidelity the anomalous fluctuations of the sun-spot curve. The ensuing minimum occurred early in 1889 and was succeeded in 1894 by a maximum slightly less feeble than its predecessor. It cannot be said that much progress has been made towards the disclosure of the cause or causes of the sun-spot cycle. No external influence adequate to the effect has at any rate yet been pointed out. Most thinkers on this difficult subject provide a quasi-explanation of the periodicity in question through certain assumed vicissitudes affecting internal processes. Sir Norman Lockyer and E. von Oppolzer reached the same end by establishing self-compensatory fluctuations in the solar atmospheric circulation. Dr. Schuster resorts to changes in the electrical conductivity of space near the sun. In all these theories, however, the course of transition is arbitrarily arranged to suit a period, which imposes itself as a fact, peremptorily claiming admittance, while obstinately defying explanation. The question so much discussed as to the influence of sunspots on weather does not admit of a satisfactory answer. The facts of meteorology are too complex for easy or certain classification. Effects owning dependence on one cause often wear the livery of another. The meaning of observed particulars may be inverted by situation, and yet it is only by the collection and collocation of particulars that we can hope to reach any general law. There is, however, a good deal of evidence to support the opinion, the grounds for which were primarily derived from the labours of Dr. Meldrum at Mauritius, that increased rainfall and atmospheric agitation attend spot maxima, while Herschel's conjecture of a more copious emission of light and heat about the same epochs has recently obtained some countenance from Sabalyev's measures showing a gain in the strength of the sun's radiation pari passu with increase in the number of spots visible on its surface. The examination of what we may call the texture of the sun's surface derived new interest from a remarkable announcement made by Mr. James Nasmyth in 1862. He had made, as he supposed, the discovery that the entire luminous stratum of the sun is composed of a multitude of elongated shining objects on a darker background, shaped much like willow leaves, of vast size, crossing each other in all possible directions, and possessed of unceasing relative motions. A lively controversy ensued. In England and abroad, the most powerful telescopes were directed to a scrutiny encompassed with varied difficulties. Mr. Dawes was especially emphatic in declaring that Nasmyth's willow leaves were nothing more than the nodules of Sir William Herschel seen under a misleading aspect of uniformity, and there is little doubt that he was right. It is nevertheless admitted that something of the kind may be seen in the penumbrae and bridges of spots, presenting an appearance compared by Dawes himself in 1852 to that of a piece of coarse straw thatching left untrimmed at the edges. The term granulated, suggested by Dawes in 1864, best describes the mottled aspect of the solar disk as shown by modern telescopes and cameras. The grains, or rather the floccules, with which it is thickly strewn, have been resolved by Langley, under exceptionally favourable conditions, into granules not above 100 miles in diameter, and from these relatively minute elements, composing jointly about one-fifth of the visible photosphere, he estimates that three-quarters of the entire light of the sun are derived. Janssen agrees so far as to say that if the whole surface were as bright as its brightest parts, its luminous emission would be 10 to 20 times greater than it actually is. The rapid changes in the forms of these solar cloud summits are beautifully shown in the marvellous photographs taken by Janssen at Meudon, with exposures reduced at times to 1/100,000th of a second. By their means also the curious phenomenon known as the réseau photosphérique has been made evident. This consists in the diffusion over the entire disk of fleeting blurred patches separated by a reticulation of sharply outlined and regularly arranged granules. The imperfect definition in the smudged areas may be due to agitations in the solar or terrestrial atmosphere, unless it be, as Dr. Schemmer thinks possible, merely a photographic effect. Monsieur Janssen considers that the photospheric cloudlets change their shape and character with the progress of the sun-spot period, but this is as yet uncertain. The grains, or more brilliant parts of the photosphere, are now generally held to represent the upper termination of ascending and condensing currents, while the darker interstices, Herschel's pores, mark the positions of descending cooler ones. In the penumbrae of spots, the glowing streams rushing up from the tremendous sub-solar furnace are bent sideways by the powerful indraft, so as to change their vertical for a nearly horizontal motion, and are thus taken, as it were, in flank by the eye, instead of being seen end-on in mamelon form. This gives a plausible explanation of the channeled structure of penumbrae which suggested the comparison to a rude thatch. Accepting this theory as in the main correct, we perceive that the very same circulatory process which, in its spasms of activity, gives rise to spots, produces in its regular course the singular marbled appearance, for the recording of which we are no longer at the mercy of the fugitive or delusive impressions of the human retina. And precisely this circulatory process it is which gives to our great luminary its permanence as a sun or warming and illuminating body. End of Chapter 2, Part 2.
Part 1 of Chapter 3 of A Popular History of Astronomy during the 19th Century. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Melanie T. A Popular History of Astronomy during the 19th Century by Agnes Mary Clerke. Chapter 3. Recent solar eclipses. By observations made during a series of 5 remarkable eclipses, comprised within a period of 11 years, knowledge of the solar surroundings was advanced nearly to its present stage. Each of these events brought with it a fresh disclosure of a definite and unmistakable character. We will now briefly review this orderly sequence of discovery. Photography was first systematically applied to solve the problems presented by the eclipsed sun, July 18, 1860. It is true that a daguerreotype taken by Bowalski with the Königsberg heliometer during the eclipse of 1851 is still valuable as a record of the corona of that year, and some subsequent attempts were made to register partial phases of solar occultation, notably by Professor Bartlett at West Point in 1854. But the ground remained practically unbroken until 1860. In that year the track of totality crossed Spain and Tiver accordingly. Warren de la Rue transported his photoheliograph and Father Secchi his 6-inch cast-shoe refractor. The question then primarily at issue was that relating to the nature of the red protuberances, although, as already stated, the evidence collected in 1851 gave a reasonable certainty of their connection with the sun. Objectors were not silenced, and when the side of incredulity was supported by so considerable an authority as Monsieur Fay, it was impossible to treat it with contempt. 2 crucial tests were available. If it could be shown that the fantastic shape suspended above the edge of the dark moon were seen under an identical aspect from two distant stations. That fact alone would annihilate the theory of optical illusion or mirage, while the certainty that they were progressively concealed by the advancing moon on one side and uncovered on the other would effectually detach them from dependence on our satellite and establish them as solar appendages. Now both these tests were eminently capable of being applied by photography, but the difficulty arose that nothing was known as to the chemical power of the rosy prominence light, while everything depended on its right estimation. A shot had to be fired, as it were, in the dark. It was a matter of some surprise and of no small congratulation that, in both cases, the shot took effect. De la Rue occupied a station at Riva Bellosa, in the upper Ebro Valley. Secchi set up his instrument at Desierto de las Palmas, about 250 miles to the southeast, overlooking the Mediterranean. From the totally eclipsed sun, with its strange garland of flames, each observer derived several perfectly successful impressions, which were found, on comparison, to agree in the most minute details. This at once settled the fundamental question as to the substantial reality of these objects, while their solar character was demonstrated by the passage of the moon in front of them, indisputably attested by pictures taken at successive stages of the eclipse. That forms seeming to defy all laws of equilibrium were, nevertheless, not wholly evanescent, appeared from their identity at an interval of 7 minutes, during which the lunar shadow was in transit from one station to the other, and the singular energy of their actinic rays was shown by the record on the sensitive plates of some prominences invisible to the telescope. Moreover, photographic evidence strongly confirmed the inference, previously drawn by Grant and others, and now with fuller assurance by Secchi, that an uninterrupted stratum of prominence matter encompasses the sun on all sides, forming a reservoir from which gigantic jets issue, and into which they subside. Thus, first fruits of accurate knowledge regarding the solar surroundings were gathered, while the value of the brief moments of eclipse gained indefinite increase, by supplementing transient visual impressions with the faithful and lasting records of the camera. In the year 1868 the history of eclipse spectroscopy virtually began, as that of eclipse photography in 1860. That is to say, the respective methods then first gave definite results. On the 18th of August 1868 the Indian and Malayan peninsulas were traversed by a lunar shadow producing total obscuration during 5 minutes and 38 seconds. 2 English and 2 French expeditions were dispatched to the distant regions favoured by an event so propitious to the advance of knowledge, chiefly to obtain the verdict of the prism as to the composition of the prominences. Nor were they dispatched in vain. An identical discovery was made by nearly all the observers. At Jamkhandi, in the Western Ghauts, where Lieutenant, now Colonel, Herschel was posted, unremitting bad weather threatened to baffle his eager expectations. But during the lapse of the critical 5½ minutes the clouds broke, and across the driving rack a long finger-like projection jutted out over the margin of the dark lunar globe. In another moment the spectroscope was pointed towards it. 3 bright lines, red, orange, and blue, flashed out, and the problem was solved. The problem was solved in the general sense that the composition out of glowing vapours of the objects infelicitously termed protuberances or prominences was no longer doubtful, although further inquiry was needed for the determination of the particular species to which those vapours belonged. Similar but more complete observations were made with less atmospheric hindrance by Tennant and Janssen at Guntoor, by Pogson at Masulipatam and by Rayet at Waton on the coast of the Malay Peninsula, the last observer counting as many as 9 bright lines. Among them it was not difficult to recognise the characteristic light of hydrogen, and it was generally, though over hastily, assumed that the orange ray matched the luminous emissions of sodium, but fuller opportunities were at hand. The eclipse of 1868 is chiefly memorable for having taught astronomers to do without eclipses, so far at least as one particular branch of solar inquiry is concerned. Inspired by the beauty and brilliancy of the various tinted prominence lines revealed to him by the spectroscope, Janssen exclaimed to those about him, "Je verrai ces longueurs-là en dehors des éclipses." On the following morning he carried into execution the plan which formed itself in his brain while the phenomenon which suggested it was still before his eyes. It rests upon an easily intelligible principle. The glare of our own atmosphere alone hides the appendages of the sun from our daily view. To a spectator on an airless planet, the central globe would appear attended by all its splendour retinue of crimson prominences, silvery corona, and far-spreading zodiacal light projected on the star-spangled black background of an absolutely unilluminated sky. Now, the spectroscope offers the means of indefinitely weakening atmospheric glare by diffusing a constant amount of it over an area widened ad libitum. But monochromatic or bright line light is, by its nature, incapable of being so diffused. It can, of course, be deviated by refraction to any extent desired, but it always remains equally concentrated in whatever direction it may be thrown. Hence, when it is mixed up with continuous light, as in the case of the solar flames shining through our atmosphere, it derives a relative gain in intensity from every addition to the dispersive power of the spectroscope with which the heterogeneous mass of beams is analysed. Employ prisms enough, and eventually the undiminished rays of persistent colour will stand out from the continually fading rainbow-tinted band by which they were at first effectually veiled. This Janssen saw by a flash of intuition while the eclipse was in progress, and this he realised at 10 a.m. the next morning, August 19th, 1868, the date of the beginning of spectroscopic work at the margin of the unobscured sun. During the whole of that day, and many subsequent ones, he enjoyed, as he said, the advantage of a prolonged eclipse. The intense interest with which he surveyed the region suddenly laid bare to his scrutiny was heightened by evidences of rapid and violent change. On the 18th of August, during the eclipse, a vast spiral structure, at least 89,000 miles high, was perceived planted in a surprising splendour on the rim of the interposed moon. If was formed, as General Tennant judged from its appearance in his photographs, by the encounter of 2 mounting torrents of flame, and was distinguished as the Great Horn. Next day it was in ruins, hardly a trace remained to show where it had been. Janssen's spectroscope furnished him besides with the strongest confirmation of what had already been reported by telescope and the camera as to the continuous nature of the Scarlet Sierra lying at the base of the prominences. Everywhere at the sun's edge the same bright lines appeared. It was not until the 19th of September that Janssen thought fit to send news of his discovery to Europe. It seemed little likely to be anticipated, yet a few minutes before his dispatch was handed to the Secretary of the Paris Academy of Sciences, a communication similar in purport had been received from Sir Norman Lockyer. There was no need to discuss the narrow and wearisome question of priority. Each of the competitors deserves and has obtained full credit for his invention. With noteworthy and confident prescience, Lockyer, in 1866, before anything was yet known regarding the constitution of the red flames, ordered a strongly dispersive spectroscope for the express purpose of viewing, apart from eclipses, the bright line spectrum which he expected them to give. Various delays, however, supervened, and the instrument was not in his hands until October 16, 1868. On the 20th he picked up the vivid rays, of which the presence and approximately the positions had in the interim become known. But there was little doubt that, even without the previous knowledge, they would have been found, and that the eclipse of August 18th only accelerated a discovery already assured. Sir William Huggins, meanwhile, had been tending towards the same goal during 2.5 years in his observatory at Tulse Hill. The principle of the spectroscopic visibility of prominence lines at the edge of an uneclipsed sun was quite explicitly stated by him in February 1868, and he devised various apparatus for bringing them into actual view, but not until he knew where to look did he succeed in seeing them. Astronomers, thus liberated by the acquisition of power to survey them at any time, from the necessity of studying prominences during eclipses, were able to concentrate the whole of their attention on the corona. The first thing to be done was to ascertain the character of its spectrum. This was seen in 1868 only as a faintly continuous one, for Rayet, who seems to have perceived its distinctive bright line far from the summits of the flames, connected it nevertheless with those objects. On the other hand, Lieutenant Campbell ascertained on the same occasion the polarization of the coronal light in planes passing through the sun's centre, thereby showing that light to be, in whole or in part, reflected sunshine. But if reflected sunshine, it was objected, the chief at least of the dark Fraunhofer lines should be visible in it, as they are visible in moonbeams, sky illumination, and all other sun-derived light. The objection was well founded, but it was prematurely urged, as we shall see. On the 7th of August 1869, a track of total eclipse crossed the continent of North America diagonally, entering at Bering Straits and issuing on the coast of North Carolina. It was beset with observers, but the most effective work was done in Iowa. At Des Moines, Professor Harkness of the Naval Observatory, Washington, obtained from the corona an absolutely continuous spectrum, slightly less bright than that of a full moon, but traversed by a single green ray. The same green ray was seen at Burlington, and its position measured by Professor Young of Dartmouth College. It appeared to coincide with that of a dark line of iron in the solar spectrum, numbered 1474 on Kirchhoff's scale. But in 1876 Young was able, by the use of a greatly increased dispersion, to resolve the Fraunhofer line 1474 into a pair, and the more refrangible member of which he considered to be the reversal of the green coronal ray. Scarcely called in question for over 20 years, the identification nevertheless broke down through the testimony of the eclipse photographs of 1898. Sir Norman Lockyer derived from them a position for the line in question notably higher up the spectrum than that previously assigned to it. Instead of 5317, its true wavelength proved to be 5303 10 millionths of a millimetre. Nor does it make any show by absorption in dispersed sunlight. The originating substance, designated coronium, of which nothing is known to terrestrial chemistry, continues luminous, at least 300,000 miles above the sun's surface, and is hence presumably much lighter even than hydrogen. A further trophy was carried off by American skill 16 months after the determination due to it of the distinctive spectrum of the corona. The eclipse of December 22nd, 1870, though lasting only 2 minutes and 10 seconds, drew observers from the New as well as from the Old World to the shores of the Mediterranean. Janssen issued from beleaguered Paris in a balloon, carrying with him the vital parts of a reflector specially constructed to collect evidence about the corona. but he reached Orion only to find himself shut behind a cloud curtain more impervious than the Prussian lines. Everywhere the sky was more or less overcast. Lockyer's journey from England to Sicily and shipwreck in the Psyche were recompensed with a glimpse of the solar aureola during 1 second and a half. 3 parties stationed at various heights on Mount Etna saw absolutely nothing. Nevertheless, important information was snatched in despite of the elements. The prominent event was Young's discovery of the reversing layer. As the surveying solar crescent narrowed before the encroaching moon, the dark lines of the spectrum, he tells us, and the spectrum itself gradually faded away until all at once, as suddenly as a bursting rocket shoots out its stars, the whole field of view was filled with bright lines more numerous than one could count. The phenomenon was so sudden, so unexpected, and so wonderfully beautiful as to force an involuntary exclamation. Its duration was about 2 seconds, and the impression produced was that of a complete reversal of the Fraunhofer spectrum, that is, the substitution of a bright for every dark line. Now, something of the kind was theoretically necessary to account for the dusky rays in sunlight which have taught us so much, and have yet much more to teach us, so that, although surprising from its transitory splendour, the appearance could not be strictly called unexpected. Moreover, its premonitory symptom in the fading out of these rays had been actually described by Secchi in 1868, and looked for by Young as the moon covered the sun in August 1869. But with the slit of his spectroscope placed normally to the sun's limb, the bright lines gave a flash too thin to catch the eye. In 1870 the position of the slit was tangential. It ran along the shallow bed of incandescent vapours instead of cutting across it. Hence his success. The same observation was made at Xeres de la Frontera by Mr. Pye, a member of Young's party, and although an exceedingly delicate one, has since frequently been repeated. The whole Fraunhofer series appeared bright, omitting other instances, to Maclear, Herschel and Fries in 1871, at the beginning or end of totality, to Pogson at the break-up of an annual eclipse, June 6, 1872, to Stone at Klipfontein, April 16, 1874, when he saw the field full of bright lines. But between the picture presented by the veritable Plus de Ligne Brillante, which descended into Monsieur Trepid's spectroscope for 3 seconds after the disappearance of the sun, May 17, 1882, and the familiar one of the dark line solar spectrum, certain differences were perceiving, showing their relation to be not simply that of a positive or negative impression. A reversing layer, or stratum of mixed vapours, glowing but at a lower temperature than that of the actual solar surface, was an integral part of Kirchhoff's theory of the production of the Fraunhofer lines. Here it was assumed that the missing rays were stopped, and here also it was assumed that the missing rays would be seen bright, could they be isolated from the overpowering splendour of their background. This isolation is effected by eclipses, with the result, beautiful confirmatory of theory, of reversing or turning from dark to bright the Fraunhofer spectrum. The completeness and precision of the reversal, however, could not be visually attested, and a quarter of a century elapsed before a successful snapshot provided photographic evidence on the subject. It was taken at Novaya Zemlya by Mr. Shackleton, a member of the late Sir George Baldwin-Power's expedition to observe the eclipse of August 9, 1896, and similar records in abundance were secured during the Indian eclipse of January 22, 1898, and the Spanish-American eclipse of May 28, 1900. The result of their leisurely examination has been to verify the existence of a reversing layer, in the literal sense of the term. It is true that no single flash photograph is an inverted transcript of the Fraunhofer spectrum. The lines are, indeed, in each case, speaking broadly, the same, but their relative intensities are widely different. Yet this need not occasion no surprise when we remember that Fraunhofer spectrum integrates the absorption of a multitudinous strata, various in density and composition, while only the upper section of the formation comes within view of the sensitive plates exposed at totalities, the low-lying vaporous beds being necessarily covered by the moon. The total depth of this glowing envelope may be estimated at 500 to 600 miles, and its normal state seems to be one of profound tranquillity, judging from the imperturbable aspect of the array of dark lines due to its sifting action upon light. The last of the 5 eclipses, which we have grouped together for separate consideration, was visible in southern India and Australia, December 12, 1871. Some splendid photographs were secured by the English parties on the Malabar coast, showing for the first time the remarkable branching forms of the coronal emanations. But the most conspicuous result was Jansen's detection of some of the dark Fraunhofer lines, long vainly sought in the continuous spectrum of the corona. Chief among these was the D line of sodium, the original index, it might be said, to solar chemistry. No proof could be afforded more decisive than this faint echoing back of the distinctive notes of the Fraunhofer spectrum, that the polariscope had spoken the truth in asserting a large part of the coronal radiance to be reflected sunlight, but it is usually so drenched in original luminosity that its special features are almost obliterated. Jansen's success in seizing them was due in part to the extreme purity of the air at Scholer in the Nightingale, where he was stationed, in part to the use of an instrument adapted by its large aperture and short focus to give an image of the utmost brilliancy. His observation, repeated during the Caroline Island eclipse of 1883, was photographically verified 10 years later by Monsieur de la Borne Pluvinel in Senegal. An instrument of great value for particular purposes was introduced into eclipse work in 1871. The slitless spectroscope consists simply of a prism placed outside the object glass of a telescope or the lens of a camera, whereby the radiance encompassing the eclipse sun is separated into as many differently tinted rings as it contains different kinds of light. These tinted rings were simultaneously viewed by Respighi at Pudacotta and by Lockyer at Baikal. Their photographic registration by the latter in 1875 initiated the transformation of the slitless spectroscope into the prismatic camera. Meanwhile, the use of an ordinary spectroscope by Herschel and Tennant at Dodder Beta showed the green ray coronium to be just as bright in a rift in the adjacent streamer. The visible structure of the corona was thus seen to be independent of the distribution of the gases which enter into its composition. By means, then, of the 5 great eclipses of 1860 to 1871, it was ascertained, first, that the prominences, and at least the lower part of the corona, are genuine solar appurtenances. Secondly, that the prominences are composed of hydrogen and other gases in a state of incandescence, and rise, as irregular outliers, from a continuous envelope of the same materials, some thousands of miles in thickness. And thirdly, that the corona is of a highly complex constitution, being made up in part of glowing vapours, in part of matter capable of reflecting sunlight. We may now proceed to consider the results of subsequent eclipses. These have raised, and have helped to solve, some very curious questions. Indeed, every carefully watched total eclipse of the sun stimulates as well as appeases curiosity, and leaves a legacy of outstanding doubt, continually, as time and inquiry go on, removed but continually replaced. It cannot be denied that the corona is a perplexing phenomenon, and that it does not become less perplexing as we know more about it. It has presented itself under quite a new and strange aspect. It presented itself under quite a new and strange aspect on the occasion of the eclipse which visited the western states of North America on July 29, 1878. The conditions of observation were peculiarly favourable. The weather was superb. Above the Rocky Mountains the sky was of such purity as to permit the detection of Jupiter's satellites with the naked eye on several successive nights. The opportunity for advancing knowledge was made the most of. Nearly 100 astronomers, including several Englishmen, occupied 12 separate posts, and prepared for an attack in force. The question had often suggested itself, and was a natural one to ask, whether the corona sympathises with the general condition of the sun, whether, either in shape or brilliancy, it varies with the progress of the sunspot period. A more propitious moment for getting this question answered could hardly have been chosen than that at which the eclipse occurred. Solar disturbance was just then at its lowest ebb. The development of spots for the month of July 1878 was represented on Wolff's system of relative numbers by the fraction 0.1, as against 135.4 for December 1870, an epoch of maximum activity. The chromosphere was, for the most part, shallow and quiescent. Its depth above the spot zones had sunk from about 6,000 to 2,000 miles. Prominences were few and faint. Obviously, if a type of corona corresponding to a minimum of sunspots existed, it should be seen then or never. It was seen, but while in some respects it agreed with anticipation, in others it completely set it at naught. The corona of 1878, as compared with those of 1869, 1870, and 1871, was generally admitted to be shrunken in its main outlines and much reduced in brilliancy. Lockyer pronounced it 10 times fainter than 1871. Harkness estimated its light at less than 1/7 that derived from the mist-blotted aureola of 1870. In shape, too, it was markedly different. When the sunspots are numerous, the corona appears to be most fully developed above the spot zones, thus offering to our eyes a rudely quadrilateral contour. The 4 great luminous sheaves forming the corners of the square are made up of rays curving together from each side into a synclinal or ogival groups, each of which may be compared to the petal of a flower. To Janssen in 1871 the eclipsing moon seemed like the dark heart of a gigantic Delia, painted in light on the sky, and the similitude to the ornament on the compass card used by Airy in 1851 well conveys the decorative effect of the beamy radiated kind of aureola. Never, it would appear, absent when solar activity is at a tolerably high pitch. In his splendid volume on eclipses, with which the systematic study of coronal structure may be said to have begun, Mr. Ranyard first generalized the synclinal peculiarity by a comparison of records. But the symmetry of the arrangement, though frequently striking, is liable to be confused by secondary formations. He further pointed out, with the help of careful drawings from the photographs of 1871 made by Mr. Wesley, the curved and branching shapes assumed by the component filaments of massive bundles of rays. Nothing of all this, however, was visible in 1878. Instead there was seen, as the groundwork of the corona, a ring of pearly light, nebulous to the eye, but shown by telescopes and in photographs to have a fibrous texture, as if made up of the tufts of fine hair. North and south, a series of short, vivid, electrical-looking flame brushes diverged with conspicuous regularity from each of the solar poles. Their direction was not towards the centre of the sun, but towards each summit of his axis, so that the farther rays on each side started almost tangentially to the surface. By the leading and a truly amazing characteristic of the phenomenon was formed by two vast, faintly luminous wings of light expanded on either side of the sun in the direction of the ecliptic. These were missed by very few careful onlookers, but the extent assigned to them varied with skill in and facilities for seeing. By far the most striking observations were made by Newcomb at Separation, Wyoming, and by Cleveland Abbey on the shoulder of Pikes Peak, and by Langley at its summit, an elevation 14,100 feet above the sea. Never before had an eclipse been viewed from anything approaching that altitude, or under so translucent a sky. A proof of the great reduction in the atmospheric glare was afforded by the perceptibility of the corona 4 minutes after totality was over. For the 165 seconds of its duration, the remarkable streamers above alluded to continued, persistently visible, stretching away right and left of the sun to a distance of at least 10 million miles. One branch was traced over an apparent extent of fully 12 lunar diameters, without a sign of definite termination having been reached, and there was no grounds for supposing the other more restricted. The resemblance to the zodiacal light was striking, and a community of origin between that enigmatical member of our system and the corona was irresistibly suggested. We should indeed expect to see, under such exceptionally favourable atmospheric conditions as Professor Langley enjoyed on Pikes Peak, the roots of the zodiacal light presenting near the sun just such an appearance as he witnessed. But we can imagine no reason why their visibility should be associated with a low state of solar activity. Nevertheless, this seems to be the case with the streamers which astonished astronomers in 1878. For in 1867, when similar equatorial emanations, accompanied by similar symptoms of polar excitement, were described and depicted by Grosch of the Santiago Observatory, sunspots were at a minimum, while the corona of 1715, which appears from the record of it by Roger Coates to have been of the same type, preceded by 3 years the ensuing maximum. The eclipse sun was seen by him at Cambridge, May 2nd, 1715, encompassed with a ring of light about 1/6 of the moon's diameter in breadth, upon which it was superposed a luminous cross formed of long bright branches lying very nearly in the plane of the ecliptic, and shorter polar arms so faint as to be only intermittently visible. The resemblance between his sketch and Cleveland Abbey's drawing of the corona of 1878 is extremely striking. It should nevertheless be noted that some conspicuous spots were visible on the sun's disk at the time of Coates' eclipse, and that the preceding minimum, according to Wolff, occurred in 1712. Thus the coincidence of the epochs is imperfect. Professor Cleveland Abbey was fully persuaded that the long rays carefully observed by him from Pikes Peak were nothing else than streams of meteorites rushing towards or from perihelion, and it is quite certain that the solar neighbourhood must be crowded with such bodies. But the peculiar structure at the base of the streamers displayed in the photographs, the curved rays meeting in pointed arches like Gothic windows, the visible upspringing tendency, the filamentous texture, speak unmistakably of the action of forces proceeding from the sun, not of extraneous matter circling round him. A further proof in the sympathetic change in the corona is afforded by analysis of its light. In 1878, the bright lines so conspicuous in the coronal spectrum in 1870 and 1871 had faded to the very limit of visibility. Several skilled observers failed to see it at all, but Young and Eastman succeeded in tracing the green coronium ray all around the sun, to a height estimated at 340,000 miles. The substance emitting it was thus present, though in a low state of incandescence. The continuous spectrum was relatively strong. Faint traces of the Fraunhofer lines attested for it an origin, in part by reflection, and polarization was undoubted, increasing towards the limb, whereas in 1870 it reached a maximum at considerable distance from it. Experiments with Edison's tachometer seem to show that the corona radiates a sensible amount of heat. End of Part 1 of Chapter 3.
Part 2, Chapter 3 of A Popular History of Astronomy During the 19th Century. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Lawrence Trask, Mount Vernon, Ohio, InterfaceAudio.com. A Popular History of Astronomy During the 19th Century by Agnes Mary Clerke. Chapter 3, Part 2. The next promising eclipse occurred May 17, 1882. The concourse of astronomers, which has become usual on such occasions, assembled this time at Sohag in Upper Egypt. Rarely have 74 seconds been turned to such account. To each observer a special task was assigned, and the advantages of a strict division of labor were visible in the variety and amount of the information gained. The year 1882 was one of numerous sunspots. On the eve of the eclipse, 23 separate maculae were counted. If there were any truth in the theory which connected coronal forms with fluctuations in solar activity, it might be anticipated that the vast equatorial expansions and polar brushes of 1878 would be found replaced by the star-like structure of 1871. This expectation was literally fulfilled. No lateral streamers were to be seen. The universal failure to perceive them, after express search in a sky of the most transparent purity, justifies the emphatic assertion that they were not there. Instead, the type of corona observed in India 11 years earlier was reproduced with its shining aigrettes, complex texture, and brilliant radiated aspect. Concordant testimony was given by the spectroscope. The reflected light derived from the corona was weaker than in 1878, while its original emissions were proportionately intensified. Nevertheless, most of the bright lines recorded as coronal were really due, there can be no doubt, to diffused chromospheric light. On this occasion, the first successful attempt was made to photograph the coronal spectrum, procured in the ordinary way with a slit and prisms. While the prismatic camera was also profitably employed, it served to bring out at least one important fact, that the uncommon strength in chromospheric regions of the twin violet beams of calcium, designated H and K, and prominence photography signalized its improvement by the registration, in the spectrum of one such object, of 29 rays, including many of the ultraviolet hydrogen series discovered by Sir William Huggins, in the emission of white stars. Dr. Schuster's photographs of the corona itself were the most extensive, as well as the most detailed of any yet secured. One rift imprinted itself on the plates to a distance of nearly a diameter and a half from the limb, and the transparency of the streamers was shown by the delineation through them of the delicate tracery beyond. The singular and picturesque feature was added of a bright comet, self-depicted in all the exquisite grace of swift movement, betrayed by the fine curve of its tail, hurrying away from one of its rare visits to our sun, and rendered momentarily visible by the withdrawal of the splendor in which it had been, and was again quickly veiled. From a careful study of these valuable records, Sir William Huggins derived the idea of a possible mode of photographing the corona without an eclipse. As already stated, its ordinary invisibility is entirely due to the glare, or reflected light diffused through our atmosphere. But Huggins found, on examining Schuster's negatives, that a large proportion of the light in the coronal spectrum, both continuous and interrupted, is collected in the violet region between the Fraunhofer lines G and H. There, then, he hoped that, all other rays being excluded, it might prove strong enough to vanquish inimical glare, and stamp on prepared plates, through local superiority in illuminative power, the forms of the appendage by which it is emitted. His experiments were begun toward the end of May, 1882, and by September 28th he had obtained a fair earnest of success. The exclusion of all other qualities of light, save that which he desired to operate, was accomplished by using chloride of silver as his sensitive material, that substance being chemically inert to all other but those precise rays in which the corona has the advantage. Plates thus sensitized received impressions which it was hardly possible to regard as spurious. Not only the general features, Captain Abney affirmed, are the same, but the details, such as rifts and streamers, have the same position and form. It was found, moreover, that the corona photographed during the total eclipse of May 6, 1883, was intermediate in shape between the coronas photographed by Sir William Huggins before and after that event, each picture taking its proper place in a series of progressive modifications, highly interesting in themselves, and full of promise for the value of the method employed to record them. But experiments on the subject were singularly interrupted. The volcanic explosion in the Straits of Sunda in August 1883 brought to astronomers a peculiarly unwelcome addition to their difficulties. The magnificent sunglows due to the diffractive effects on light of the vapors and fine dust flung in vast volumes into the air and rapidly diffused all around the globe betokened an atmospheric condition of all others the most prejudicial to delicate researches in the solar vicinity. The filmy coronal forms, accordingly, which had been hopefully traced on the Tulse Hill plates, ceased to appear there, nor were there any substantially better results obtained by Mr. C. Ray Woods in the purer air either of the Riffel or the Cape of Good Hope during the 3 ensuing years. Moreover, attempts to obtain coronal photographs during the partial phases of the eclipse of August 29, 1886, completely failed. No part of the lunar globe became visible in relief against circumfluous solar radiance on any of the plates exposed to Granada, and what vestiges of structure there were came out almost better upon the moon than beside her, thus stamping themselves at once as of atmospheric origin. That the effect sought is a perfectly possible one is proved by the distinct appearance of the moon projected on the corona in photographs of the partially eclipsed sun in 1858, 1889, and 1890, and very notably in 1898 and 1900. In the spring of 1893, Professor Hale attacked the problem of coronal daylight photography, employing the double-slit method so eminently serviceable for the delineation of prominences. But neither at Kenwood nor at the summit of Pike's Peak, whither in the course of the summer he removed his apparatus, was any action of the desired kind secured. Similar ill success attended his and Professor Rico's employment on Mount Etna in July 1894 of a specially designed coronagraph. Yet discouragement did not induce despair. The end in view is indeed too important to be readily abandoned, but it can be reached only when a more particular acquaintance with the nature of coronal light than we now possess indicates the appropriate device for giving it a preferential advantage in self-portraiture. Moreover, the effectiveness of this device may not improperly be enhanced through changes in the coronal spectrum at epochs of sun-spot maximum. The prosperous result of the Sohag observations stimulated the desire to repeat them on the first favorable opportunity. This offered itself 1 year later, May 6, 1883, yet not without the drawbacks incident to terrestrial conditions. The eclipse promise was of rare length, giving no less than 5 minutes and 23 seconds of total obscurity, but its path was almost exclusively a water track. It touched land only on the outskirts of the Marquesas group in the southern Pacific, and presented, as the one available foothold for observers, a coral reef named Caroline Island, 7½ miles long by 1½ wide, unknown previously to 1874, and visited only for the sake of its stores of guano. Seldom has a more striking proof been given to the vividness of human curiosity as to the condition of the worlds outside our own than in the assemblage of a group of distinguished men from the chief centers of civilization on a barren ridge, isolated in a vast and tempestuous ocean, at a distance in many cases of 11,000 miles and upwards from the ordinary scene of their labors. And all these sacrifices, the cost and care of preparation, the transport and readjustment of delicate instruments, the contrivance of new and more subtle means of investigating phenomena, on the precarious chance of a clear sky during one particular 5 minutes. The event, though fortunate, emphasized the hazard of the venture. The observation of the eclipse was made possible only by the happy accident of a serene interval between two storms. The American expedition was led by Professor Edward S. Holden, and to it were courteously permitted to be attached Messrs. Lawrence and Woods, photographers, sent out by the Royal Society of London. Monsieur Johnson was chief of the French Academy mission. He was accompanied by Moudon, by Trevor, and joined from Vienna by Palisa, and from Rome by Tacchini. A large share of the work was directed to assuring or negativing previous results. The circumstances of an eclipse favor illusion. A single observation by a single observer, made under unfamiliar conditions and at a moment of peculiar excitement, can scarcely be regarded as offering more than a suggestion for future inquiry. But incredulity may be carried too far. Johnson, for instance, felt compelled, by the survival of unwise doubts, to devote some of the precious minutes of obscurity at Caroline Island to confirming what, in his own persuasion, needed no confirmation, that is, the presence of reflected Fraunhofer lines in the spectrum of the corona. Trouvelot and Palisa, on the other hand, instituted an exhausted but fruitless search for the spurious intramercurian planets announced by Swift and Watson in 1878. New information, however, was not deficient. The corona proved identical in type with that of 1882, agreeably to what was expected at an epoch of protracted solar activity. The characteristic aigrettes were of even greater brilliancy than in the preceding year, and the chemical effects of the coronal light proved unusually intense. Johnson's photographs, owing to the considerable apertures, 6 and 8 inches, of his object glasses, and the long exposures permitted by the duration of totality, were singularly perfect. They gave a greater extension to the coronal than could be traced with the telescope, and showed its forms as absolutely fixed and of remarkable complexity. The English pictures, taken with exposures up to 60 seconds, were likewise of great value. They exhibited details of structure from the limb to the tips of the streamers, which terminated definitely, and, as it seemed, actually, where the impressions on the plates ceased. The coronal spectrum was also successfully photographed, and although the reversing layer in its entirety evaded record, a print was caught of some of its more prominent rays just before and after totality. The use of the prismatic camera was baffled by the anomalous scarcity of prominences. Using an ingenious apparatus for viewing simultaneously the spectrum from both sides of the sun, Professor Hastings noticed at Caroline Islands alternations with the advance of the moon in respective heights above the right and left solar limbs of the coronal green line, which were thought to imply that the corona, with its rifts and sheaves and tangled hanks of rays, is, after all, merely an illusive appearance, produced by the diffraction of sunlight at the moon's edge. But the observation was assuredly misleading or misinterpreted. Atmospheric diffusion may indeed, under favoring circumstances, be effective in deceptively enlarging solar appendages, but always to a very limited extent. The controversy is an old one, as to the part played by our air in producing the radiance visible round the eclipsed sun. In its original form, it is true, it came to an end when Professor Harkness, in 1869, pointed out that the shadow of the moon falls equally over the air and on the earth, and that if the sun had no luminous appendages, a circular space of almost absolute darkness would consequently surround the apparent places of the superposed sun and moon. Mr. Proctor, with his usual ability, impressed this mathematically certain truth upon public attention, and Sir John Herschel calculated that the diameter of the negative halo thus produced would be in general no less than 23 degrees. But about the same time a noteworthy circumstance relating to the state of things in the solar vicinity was brought into view. On February 11, 1869, Messrs. Franklin and Lockyer communicated to the Royal Society a series of experiments on gaseous spectra under varying conditions of heat and density, leading them to the conclusion that the higher solar prominences exist in a medium of excessive tenuity, and that even at the base of the chromosphere the pressure is far below that at the Earth's surface. This inference was fully borne out by the researches of Wüllner and Janssen, expressed the opinion that the chromospheric gases are rarefied almost to the degree of an air-pump vacuum. Hence was derived a general and fully justified conviction that there could be outside and incumbent upon the chromosphere no such vast atmosphere as the corona appeared to represent, upon the strength of which conviction the glare theory entered, chiefly under the auspices of Sir Norman Lockyer, under the second stage of its existence. The genuineness of the inner corona, to the height of 5 feet or 6 feet from the limb, was admitted, but it was supposed that by the detailed reflection of its light in our air, the far more extensive outer corona was optically created, the irregularities of the moon's edge being called into account for the rays and rifts by which the structure was varied. This view received some countenance from Admiral Maclear's observation, during the eclipse of 1870, of bright lines everywhere, even at the center of the lunar disk. Here indeed was an undoubted case of atmospheric diffusion, but here also was a safe index to the extent of its occurrence. Light scatters equally in all directions, so that when the moon's face at the time of an eclipse shows, as is the common case, a blank in the spectroscope, it is quite certain that the corona is not noticeably enlarged by atmospheric causes. A sky drifted over with thin cirrus clouds and air changed with aqueous vapor amply accounted for the abnormal amount of scattering in 1870. But even in 1870, positive evidence was obtained of the substantial reality of the radiated outer corona, in the appearance on photographic plates exposed by Willard in Spain and by Brothers in Sicily, of identical dark rifts. The truth is that far from being developed by misty air, it is peculiarly liable to be affected by it. The purer the sky, the more extensive, brilliant, and intricate in the details of its structure the corona appears. Take as an example General Meyer's description of the eclipse of 1869, as seen from the summit of White Top Mountain, Virginia, at an elevation above the sea of 5,523 feet, in an atmosphere of peculiar clearness. To the unaided eye, he wrote, the eclipse presented, during the total obscuration, a vision magnificent beyond description, as a center stood the full and intensely black disk of the moon, surrounded by the aureola of a soft bright light, through which shot out, as if from the circumference of the moon, straight massive silvery rays, seeming distinct and separate from each other, to a distance of 2 or 3 diameters of the solar disk, the whole spectacle showing as on a background of diffused rose-colored light. On the same day at Des Moines, Newcomb could perceive, through somewhat hazy air, no long rays, and the 4-pointed outline of a corona reached at its farthest only a single semi-diameter of the moon from the limb. The plain fact that our atmosphere acts rather as a veil to hide the coronal radiance than as the medium through which it is visually formed emerges from further innumerable records. No observations of importance were made during the eclipse of September 9th, 1885. The path of total obscurity touched land only on the shores of New Zealand, and 2 minutes was the outside limit of available time. Hence local observers had the phenomenon to themselves, nor were they even favored by the weather in their efforts to make the most of it. One striking appearance was, however, disclosed. It was that of two white prominences of unusual brilliancy, shining like a pair of electric lamps, hung one at each end of a solar diameter, right above the places of two large spots. This coincidence of diametrically opposed disturbances is of too frequent occurrence to be accidental. Monsieur Trouvelot observed at Meudon in June 26, 1885, two active and evanescent prominences thus situated, each rising to an enormous height of 300,000 miles, and on August 16th, one scarcely less remarkable, balanced by an antipodal spot group. It towered upward, as if by a process of unrolling, to 250,000 miles, after which, in 2 minutes, the light died out of it. It had become completely extinct. The development, again from the ends of a diameter, of a pair of similar objects, was watched September 19th and 20th, 1893, by Father Figny, director of the Coloxa Observatory, and the phenomenon has been too often repeated to be accidental. The eclipse of August 29th, 1886, was total during about 4 minutes over tropical Atlantic regions, and an English expedition, led by Sir Norman Lockyer, was accordingly dispatched to Grenada in the West Indies, for the purpose of using the opportunity it offered. But the rainy season was just then at its height. Clouds and squalls were the order of the day, and the elaborately planned program of observation could only in part be carried through. Some good work none the less was done. Professor Tacchini, who had been invited to accompany the party, ascertained, besides some significant facts about prominences, from a comparison of their forms and sizes during and after the eclipse, it appeared that only the growing vaporous cores of these objects were shown by the spectroscope under ordinary circumstances, their upper sections giving a faint continuous spectrum, and composed of presumably cooler materials, can only be seen when the veil of scattered light usually drawn over them is removed by an eclipse. Thus all modestly tall prominences have silvery summits, but all do not appear to possess the red heart of flame by which alone they can be rendered perceptible to daylight observation. Some prove to be ordinarily invisible, because silvery throughout, sheeted ghosts, as it were, met only in the dark. Specimens of the class had been noted as far back as 1842, but Tacchini first drew particular attention to them. The one observed by him in 1886 rose in a branching form to a height of 150,000 miles, and gave a brilliantly continuous spectrum, with bright lines at H and K, but no hydrogen lines. Hence the total invisibility of the object before and after the eclipse. During the eclipse it was seen framed, as it were, in a pointed arch of coronal light, the symmetrical arrangement of which, with regard to it, was obviously significant. Both its unspringing shape and the violet rays of calcium strongly emitted by it contradicted the supposition that white prominences represent a downrush of refrigerated materials. The corona of 1886, as photographed by Dr. Schuster and Mr. Maunder, showed neither the petals and plumes of 1871 nor the streamers of 1878. It might be called of a transition type. Wide polar rifts were filled in with tufted radiations, and bounded on either side by irregularly disposed compound luminous masses. In the southwestern quadrant, a triangular ray, conspicuous to the naked eye, represented, Mr. W. H. Pickering thought, the projection of a huge hollow cone. Branched and recurving jets were curiously associated with it. The intrinsic photographic brightness of the corona proved, from Pickering's measures, to be about 1/54th that of the average surface of the full moon. The Russian eclipse of August 19, 1887, can only be remembered as a disastrous failure. Much was expected of it. The shadow path ran from overland from Leipzig to the Japanese Sea, so that the solar appurtenances would, it was hoped, be disclosed to observers echeloned along a line of 6,000 miles. But the incalculable element of weather rendered all forecasts nugatory. The clouds never parted during the critical 3 minutes over central Russia, where many parties were stationed, and Professor D.P. Todd was equally unfortunate in Japan. Some good photographs were nevertheless secured by Professor Harari, director of the Tokyo Observatory, as well as by M. Belopolsky and Glaisnapp at Petrovolsk and Jurjevich, respectively. They showed a corona of simpler form than that of the year before, but not yet of the pronounced type first associated by Mr. Regnard with the lowest stage of solar activity. The genuineness of the association was ratified by the duplicate spectacle of the next ensuing minimum year. 2 total eclipses of the sun distinguished 1889. The first took place on New Year's Day, when a narrow shadow path crossed California, allowing less than 2 minutes for the numerous experiments prompted by the varied nature of modern methods of research. American astronomers availed themselves of the occasion to the full. The heavens were propitious. Photographic records were obtained in unprecedented abundance and of unusual excellence. Their comparison and study placed it beyond reasonable doubt that the radiated corona belonging to periods of maximum sunspots gives place at periods of minimum to the winged type of 1878. Professor Holden perceived further that the equatorial extensions characterizing the latter tend to assume a trumpet shape. Their extremities diverge as if mutually repellent, instead of flowing together along a medial plane. The maximum actinic brilliancy of the corona, January 1, 1889, was determined at Lick to be 21 times less than that of the full moon. Its color was described as of an intense luminous silver, with a bluish tinge, similar to the light of an electric arc. Its spectrum was comparatively simple. Very few bright lines, besides those of hydrogen and coronium, and apparently no dark ones, stood out from the prismatic background. The marked structural features of the corona, as presented by the negatives taken by Professors Neiffer and Sheropin, were the filaments and streamers. The filaments issued from polar calottes of 20-degree radius. The impression conveyed to the eye, Professor Pritchard wrote, is that the equatorial stream of denser coronal matter extends across and through the filaments, simply obscuring them by its greater brightness. The effect is just as if the equatorial belt were superposed upon or passed through the filamentary structure. There is nothing in the photographs to prove that the filaments do not exist all around the sun. The testimony from negatives of different lengths of exposure goes to show that the equatorial streamers are made up of numerous interlacing parts, inclined at various angles to the sun's equator. The coronal extensions, perceptible with the naked eye to a distance of more than 3 degrees from the sun, appeared barely 1/3 of that length on the best negatives. Little more could be seen of them either in Barnard's exquisite miniature pictures or in the photographs obtained by W. H. Pickering with a 13-inch refractor, the largest instrument so far used in eclipse photography. End of Chapter 2, Part 2. Recording by Lawrence Trask. InterfaceAudio.com, Mount Vernon, Ohio.